This is Unit 10, and this unit will be an introduction to structural equation modeling, and we will look at how we can use structural equation modeling to test discriminant validity. Now, recall that the usual way for testing discriminant validity, which is an approach that I really do not like, but the usual approach is simply to take a scale I want to validate and show that my scale fails to correlate with something it's not supposed to correlate with. So, for example, if I have an adversarial engagement scale, a self-report questionnaire that measures how much people use hostile or critical types of communication when they have a conflict with a romantic partner. And if I think that adversarial engagement should not really correlate that much with depression, I could test discriminant validity by just doing a study where I measure adversarial engagement and I measure depression, and then I just run a correlation to see how much they're correlated. And in this case, I do not want a correlation because I think they should be distinct. So a non-significant correlation would be evidence of discriminant validity, whereas a significant correlation would be evidence that I fail to have discriminant validity. In other words, it's a significance test turned upside down on its head, where I want things to be non-significant and I don't want things to be significant. So in this example, I have a sample of 310 people, and when I tested the correlation between depression and adversarial engagement, I got a correlation of 0.16, which was a very small correlation, but my sample of 310 people, that was big enough to still make this a significant correlation. So if I'm using the usual approach, if I'm following the usual approach for testing discriminant validity, I would say I have a significant correlation, and because it's significant, I have failed to demonstrate discriminant validity, because what I really wanted was a non-significant correlation. Now, one problem with this is just the issue that it's kind of unreasonable to think that depression and adversarial engagement would have a zero correlation. But another problem, and really the big problem with this, is that I have a test that's based on sample size. And so if I have a small sample, then just about everything's going to be non-significant. And if I have a huge sample, just about everything's going to be significant. I'm not so much testing discriminant validity as I am testing the size of my sample. And so this really isn't a good way to provide useful information about the discriminant validity of the scale, at least from my opinion. Even though it's the usual approach, it certainly has problems. Now, a better approach to testing discriminant validity, from my opinion, is to do something that involves making a comparison. So instead of taking the scale that I want to validate and saying that my scale should correlate 0 with something, I'll say that the correlation should be smaller than some other comparison correlation. So, for example, say I want to validate a collaborative engagement scale. This would be a self-report questionnaire measuring the extent to which people have positive, constructive approaches towards communication when they have a conflict with a romantic partner. And I think that collaborative engagement should produce a relatively moderate or small correlation with perceived threat, which is when people have a conflict, it's how much they feel threatened by a partner, how much they feel that their autonomy is being threatened, or they feel challenged by their partner. So I think that collaborative engagement should be relatively weakly associated with perceived threat compared to, for example, adversarial engagement, which should have a much stronger association with perceived threat. So my hypothesis is that the relationship between collaborative engagement and perceived threat should be relatively weak. The association between adversarial engagement and perceived threat should be relatively strong. So now I'm not claiming that a correlation should be 0. I'm just claiming that my correlation should be weaker than something else that I'm comparing it to. And this gives me a lot of flexibility in the types of questions I want to address here. So in this particular example, it turned out that the correlation between adversarial engagement and perceived threat was 0.64, and the correlation between collaborative engagement and perceived threat was negative 0.38. Now, note that our key question here has to do with a difference between correlations in their absolute values. That is, a difference between correlations in the overall magnitude of effect. I really don't care if the correlations are positive or negative. Note that I could actually flip the sign of a correlation simply by reverse coding all the items on a scale. I could take my collaborative engagement scale and score it so that a high score means low collaborative engagement and a low score means high collaborative engagement, and then that would change the direction of the correlation. It wouldn't make any sense to do it that way, but that just illustrates the fact that the direction of the correlation, positive or negative, has to do with how you scaled your scale. And in this case, what we really care about is absolute values, not the direction that we scaled our instrument in. So when I compare two correlations, I'm going to compare absolute values. I'm going to remove the negative signs. So I'll take my correlation 0.64 minus 0.38, and I've removed the negative sign, so just 6.64, the difference between these two correlations, and the difference is 0.26. Now, that would support my hypothesis. That's going in the right direction, showing that the correlation with adversarial engagement perceived threat, that's a bigger correlation, and the collaborative engagement perceived threat correlation is smaller in magnitude. That fits my hypothesis. But the question is this a significant difference? I mean, at this point, it's entirely possible that maybe I replicate my study another time, and maybe the next time the collaborative engagement correlation is bigger and the adversarial engagement correlation is smaller. They might flip back and forth if I do my study over and over again. So just because it came out that this correlation was bigger in this study, it doesn't mean that that's really a bigger correlation if I replicate my study over and over again. So the question is this difference between my two correlations, is this difference in magnitude of effect, is that a significant difference? And it turns out we can test that. We can do a t-test, which I will show you in a moment. In this particular example, I ran a t-test, and I did get the t was 8.6, and this was significant, showing that we did indeed have a significant difference between these two correlations in magnitude of effect, which could be taken as evidence of support for discriminant validity. So for this unit, we're going to be talking about ways that we can be testing for significant differences between two effects. What I was just talking about was a situation where I wanted to see if there was a difference between two correlations. And in just a moment, I'll show you how we can use a hand calculation to calculate a t-value that will test for a difference between two correlations. After we do that, we're going to go on to talking about structural equation modeling, which will be the majority of this unit. And we're going to look at how we could run a regression equation where we have two predictors of an outcome and we can test for a difference between two beta weights. And that's something we can do if we're running regression using structural equation modeling, or SEM for structural equation modeling. So before we get to the structural equation modeling approach, let's start with looking at how we can test for a difference between two correlations with a hand calculation t-value formula. So here is a formula you can use to do a t-test to test for a difference between the magnitude of effect between two different correlations. Now this is kind of a large, complex formula, and I actually would never expect you to memorize it. When I use this formula myself, actually I have an Excel file where I've put in all the equations so that I can just type in the values for my correlations and get the output. And you will need to run this type of test when you do your projects, and for that you can actually just use the R package. R has a package that will test for a difference between two correlations for you, which makes it really easy. The key thing to note when using this formula, whether you're doing this by hand or if you're using the R version, is to note how these correlations have been labeled. So here I have, it says T, we're going to get a t-test for a difference between two correlations, and I'm going to call these correlations with a subscript 1, 2, and R with a subscript 1, 3. So I have correlation 1, 2 and correlation 1, 3. And what this is testing for is a difference between two correlations when I'm looking at how two different variables correlate with a common outcome. So in these equations, 1 is a common outcome. That would be the criterion variable. And 2 and 3 represent the two target scales that I'm looking for a difference between. Let me back up to a previous slide. Here's the slide when I talked about discriminant validity. So we're looking at how, so we could say that perceived threat is the common outcome. So that'll be variable 1, perceived threat. And then if I have adversarial engagement as one of my predictors, I'll call that 2. And collaborative engagement is another one of my predictors, so I'll call that 3. So I have one correlation, I'll call the correlation 1, 2, will be the correlation between perceived threat and adversarial engagement. And correlation 1, 3 will be the correlation between perceived threat and collaborative engagement. So again, on my slide here, I've got correlation 1, 2 and correlation 1, 3. And for example, up here, one of the things you also need to know is what is a correlation 2, 3. That's the correlation between my two different scales I'm validating. So in my current example, that would be the correlation between adversarial engagement and collaborative engagement. So we need to know all three of these correlations actually to plug in values for this formula. And also, if it's calculated in R, you would also still need to know the values for all three of these correlations to get your t-value. And once you plug all this in, you get a t-value, and then your total degrees of freedom are going to be n minus 3. And then you could look it up on any t table, or go get an online t calculator and determine if your t-value with n minus 3 degrees of freedom is significant. And that is how to calculate a t-test for a difference between two correlations. Okay, now we're ready for the fun stuff. And I'm going to give you an introduction to structural equation modeling, and then we'll look at how we can use structural equation modeling to test for a difference between two beta weights in the magnitude of their effect. So first, what exactly is structural equation modeling? You can think of structural equation modeling as kind of a souped up fancy approach to doing regression that can actually do quite a bit more than what we could do with a regular approach to regression. So that means the easiest way to explain what structural equation modeling is to start with a basic regression equation and see how we can estimate that equation using a structural equation modeling approach, or an SEM approach. So up at the right, I have a regression equation where I say y hat. We're going to do a multiple regression equation where I have one outcome and three predictors. So I'll say y hat is equal to a slope times x1 plus a slope times x2 plus a slope times x3. Now, one thing I'm going to do when I'm talking about structural equation modeling, and I'll do that throughout this entire rest of this unit, is I'm just going to assume that I've standardized all my variables prior to analysis. I'm going to assume that I've turned everything to z-scores prior to analysis. And when I make that assumption, what that means is that my regression equations will not have intercepts. Recall that if I turn everything to z-scores prior to analysis, my intercept simply becomes 0. And so if I assume all my variables are z-scores, I don't have to bother with putting intercepts in my models. So that's my model simplifies then to y hat is equal to no intercept, I'm sorry. Y hat is not. Y hat is equal to slope times x1 plus slope 2 times x2 plus slope 3 times x3. And of course, if we wanted to, we could rewrite our equation without the hat. If I could take that off, hat gone. That's all gone. And then I'll put a plus e at the end here. And we could rewrite our equation that way if we wanted to. Two ways of writing the same equation. So that's our basic regression equation. Now, when we're doing structural equation modeling, there's many ways to think about what we're doing, but one of the most common ways, and one of the ways that makes it easiest to understand, is to draw pictures. So it's very, very common when people do structural equation modeling to draw pictures of the models that we're estimating. And there's a common format that people always use when they draw these pictures. And so what we're going to do, we're going to put variables in boxes, and we're going to put parameter estimates outside those boxes. So what I have here, the rest of the slide has the picture for this regression equation. And it shows that I have three variables in these boxes, x1 and x2 and x3, and they're each variables in a box. And keep in mind that a variable, if I do a study, and say I get a sample of 100 people, x is a variable. It means that every single person in my sample can have a different score on x. Y is a variable. It means that every single person in my sample can have a different score on y. Then I'll have parameters or parameter estimates, and I'll have one parameter estimate for my entire sample. So for example, my slope for x1, that's a parameter estimate, and there's just one slope for my entire sample, whereas every single person can have a different score on x1. And likewise, Beta 2 is a different parameter, so there'll be one estimate for beta 1, there'll be one estimate for beta 2, and one estimate for beta 3. So in this case, I've got 3 parameter estimates, and I'll get just one of each for my entire sample. But every single person in my sample will have a different score in X, or at least they can, and every single person will have a different score in Y. So variables are things that can change from one person to the next. The parameter estimates are things that are based on my entire sample, and I only have one of each parameter estimate. So if I have 3 betas, I'll have one parameter estimate for beta 1, one for beta 2, and one for beta 3. So what my model is showing is that I put my variables in boxes, and then a straight line with an arrow is going to indicate a regression relationship. Actually, when we use the language of regression, we would usually say that Y is regressed on X, if you want to use the language appropriately, or we could say that X predicts Y. So Y regressed on X, or X predicts Y are two ways of saying the same thing. So if I think that X predicts Y, I draw the straight line with an arrow from X pointing to Y, saying that X1 predicts Y. And so this picture is showing that X1, X2, and X3 all have straight lines pointing to Y. So I have a regression equation with 3 predictors. And then I put my betas on top of the lines, showing that this line will have a beta. That will be the slope for X1. And the middle line will have a beta. That will be the slope for X2. And the bottom line will have a beta. That will be the slope for X3. And then in my model, I've also drawn some curved, not straight, some arched lines that have 2 arrows, one on each side. And I've actually got 3 of those, and those are going to indicate correlation. So I'm going to say that X1 can also correlate with X2, X2 can correlate with X3, and X1 can correlate with X3. In other words, we can run a correlation matrix and get those correlations. And note that that's the stuff that when I've had you running regression equations, I've often had you run correlations between variables and get that correlation matrix, and then run your regression equation and get your beta weights. And so this model is showing you both all at once, showing you we've got correlations between variables, and we've got our regression slopes from our regression equation. So that's how we can draw the model for an SEM approach, a model for a regression equation. Okay, before we proceed, let's review how we would calculate intercepts and slopes and correlations. Recall that the slope from a regression equation is simply equal to a covariance divided by the variance of x. And the variance is simply your standard deviation squared, or standard deviation x times itself. And a correlation is a covariance divided by the standard deviation of x times the standard deviation of y, the product of your 2 standard deviations. And that product of your 2 standard deviations is simply a measure of averaged variance. It's actually the geometric mean of your variances. So a slope is a covariance divided by the variance of x, and a correlation is a covariance divided by the averaged variance of x and y. And then if we wanted to calculate the intercept, we'd get the mean of y and subtract from that our slope times the mean of x. Now note that, let's look down here at our slopes and correlations, betas and correlations. Note that everything we need to calculate a slope or a correlation we can get from a variance covariance matrix. Our variance covariance matrix gives us variances, and if we square those, we'll have standard deviations, so we can get standard deviations. And if we have standard deviations and variances and covariances from our variance covariance matrix, we can calculate our slope. We get our covariance and our variance, and our covariance divided by a product of our 2 standard deviations. We can get all that information simply from a variance covariance matrix. So if I have a variance covariance matrix, I could calculate my slope and I could calculate my correlation. Now, the variance covariance matrix by itself would not allow me to calculate intercepts, but if I also had the means from my variables and a variance covariance matrix, then I could calculate an intercept. So if I wanted to calculate slopes and correlations, all I need is a variance covariance matrix. If I also wanted to calculate intercepts, I would need that variance covariance matrix, plus I would need to know the means for my variables, and then I could estimate my intercept. So the process to doing structural equation modeling is going to involve first starting with a variance covariance matrix and inputting that variance covariance matrix into our program, and then using that variance covariance matrix to produce our parameter estimates, things like our betas, our slopes. And there's two ways we can go about doing that. The typical and most common approach to structural equation modeling uses only a variance covariance matrix, and an optional approach that we sometimes take, but not all that often, is where we use a variance covariance matrix and also the means for our variables that will allow us to produce models with intercepts. So the typical approach then, the typical approach to SEM, we're going to estimate models. We'll simply start with a variance covariance matrix and nothing else. All we need to run our analysis, we need to know what the variance covariance matrix is between our variables. And once I have that variance covariance matrix, I could input that into a structural equation modeling program, and it can produce all the output that I need simply from that variance covariance matrix. When I'm doing this, I'm going to get a model. My equations will have no intercepts in them, and we're going to be running models with variables that are centered. We're going to be assuming that our variables are centered so that they have means of 0. And actually, we only need to assume that they've been centered and not necessarily turned into z-scores. Recall that the process of turning a score into a z-score has 2 steps. First, you center it, you subtract the mean from everybody's score, and you have a new score that has a mean of 0. And then the second step is to divide that centered score by a standard deviation. And then everybody has a new score that will have a mean of 0 and a standard deviation of 1. So for structural equation modeling, we really only need to do that first step. We need to center all the variables so we have a new score that has a mean of 0, and that is all that is needed to make our intercepts drop out of our equations. That will make all of our intercepts 0, and that will give us equations that have no intercepts. But to simplify things and to make things easy to understand and consistent throughout this unit, I'm going to just always assume we've taken things one step further and that we've turned everything into z-scores. So I'm just going to assume we're just always working with z-scores. So that is a typical approach to SEM. Now, in some rare situations, we actually do want to have intercepts in our models. And if we do that, then we need to input into our SEM program. We need both a variance covariance matrix and we need to know the means for all of our variables. And we take our means and our variance covariance matrix, enter that into a program, and we'll get a model that has intercepts if that's what we need. So those are the 2 basic approaches. So what I'm going to be doing with structural equation modeling is using a variance covariance matrix to estimate parameters for my structural equation model. In this example we've been looking at, where I have a basic regression equation where I've got 3 x variables predicting a y variable, we have actually 6 different parameters that we could estimate here. We've got 3 beta weights, beta 1, beta 2, beta 3, and we've also got 3 correlations, the correlation between x1 and x3, the correlation between x2 and x1, between x2 and x3. So we've got 3 correlations and 3 beta weights. So we have 6 different parameters altogether that we might want to estimate in this analysis. And we're going to estimate these 6 parameters from a variance covariance matrix that has 6 covariances in it. Because I've got 4 variables altogether, x1, x2, x3, and then also y. So that's 4 variables altogether. And if I have a 4 by 4, 1, 2, 3, y, 1, 2, 3, y, 4 by 4 variance covariance matrix, how many covariances are in that matrix? I've got 6. And I could do 6 below the diagonal. If I wanted to, I could put them above the diagonal. It would be the same mirror image above and below that diagonal. I've got 6 different covariances. The covariance between x1 and x2, between x1 and x3, between x1 and y, and so forth. So I've got 6 total different covariances. So I'm trying to estimate 6 parameters from 6 covariances, which works out nice and neat that way. And actually, if I'm trying to estimate 6 things from 6 things, that is a feasible, possible thing to do. Now, in addition to those 6 parameters, I also have variance components that need to be estimated in my structural equation model. That is, I have a variance of x1. It's going to have a standard deviation, or a squared standard deviation will be its variance. I'll have x2, and it will have a standard deviation, or a squared standard deviation will be its variance. And x3 will also have a variance. And then for y, when I'm doing structural equation modeling, I'm actually not going to care so much about the variance of y as I will care about its residual variance, or that is the standard error of estimate. If I use my x variables to predict y, how far does observed y typically deviate from predicted y? That is, what is the residual in y after I've used x1 to predict y? Or you could say it this way: what is the residual in y after my 3 x variables have been extracted out of it? Those are all different ways of describing the same thing, which is our standard error of estimate, which is also sometimes called our residual variance of y. So I've got these 4 variance components. If I have an x variable that's predicting y, I'm just going to ask what its variance is. If I have an outcome variable y, instead of asking what its variance is, I'm going to focus on what is its standard error of estimate. That is, what is the residual variance. And note, once again, I've got a situation where I'm wanting to estimate 4 things. I've got my variance of x1, x2, x3, and the residual variance of y. So there's 4 variance components that I need to estimate in my model. And my variance covariance matrix has 4 variance components in it. I've got these 4 variance components in my variance covariance matrix to estimate the variance components in my model. So far things are working out very neat. The number of things we need to estimate in our model is identical to the number of things we have in our variance covariance matrix. Now, one thing we can do when we're doing structural equation modeling is we're not limited to doing just one equation at a time. We can run models that might estimate multiple equations. We can simultaneously estimate multiple equations. So this picture I have here is actually illustrating 2 different equations. If you look at it carefully and see what's going on in it, maybe you can pick out how we have 2 different equations embedded in this picture. So one part of this picture is the same exact model that I've been showing you all along, where I'm predicting y using 3 variables. Here I have x1. I'm going to, instead of calling that x2, I'll call that m, maybe for mediator, and x3. So I've got 3 variables predicting y. And that's the same equation we've been looking at all along, where I say y hat is equal to slope 1 times x1, slope 2 times, now I'm calling this m for mediator rather than x2, and slope 3 times x3. But that's the same equation we've been looking at all along. The only thing that's different is that I've added these extra arrows, and rather than looking at a correlation here, I've changed and I'm saying x1 predicts m and x3 predicts m. So I've got this equation where I say m is, the predicted m is equal to this slope 4 times x1 plus this slope 5, this beta 5, times x3. So this picture that I have on the left has 2 regression equations embedded in it. And as we'll see, we can run models that would estimate all these parameters all at once. That's one thing we get when we will be doing structural equation modeling. It's an approach that would allow us to estimate these types of equations where I have a model with multiple equations embedded in it, and we can simultaneously estimate all the parameters that we need for all these equations. And that's not all we can do with structural equation modeling. Another especially important thing we can do is that we can put constraints on our models. So up in the upper right hand corner, I have all these different parameters that I talked about that we can estimate when we do a structural equation model. The things we can estimate from our variance covariance matrix. So we can estimate our, I've gone back to my my single regression equation that has 3 different slopes, 3 different beta weights, and in this model I have 3 correlations, and I've got 4 variance components. And so any of those things, any of these parameter estimates, including the variance components, I could put a constraint on any of those. What do I mean by putting a constraint on something? How does that work? What am I talking about? So, for example, one type of constraint I could do is that I could constrain a parameter to be 0. I could say it doesn't exist or it's not theoretically relevant. To think about this, recall what we were talking about in our previous unit about mediation and what a mediation pathway is. So if we look at this part of our equation right here, we've got an x predicting y and a mediator, and we could say this pathway right here, beta 1, that would be the direct effect of x1 on y. After controlling for the mediator, how much does x1 still have a direct effect on y, controlling for the mediator? And then we've got this mediated path where x1 predicts the mediator, which in turn predicts y. And so if I constrain beta 1 to be 0, what I'm saying is I've got a model where there's a fully mediated relationship between x1 and y. That the relationship between x1 and y is fully explained by this mediator, and after controlling for this mediated pathway, after controlling for the extent to which x1 predicts m, which in turn predicts y, after controlling for that pathway, there's no remainder, no residual direct effect of x1 on y. The effect is fully explained by the mediator, and there's no direct effect. So if I constrain this beta weight here to be 0, if I constrain beta 1 to be 0, that I've created a model where I'm hypothesizing, it's a model testing a full mediation where x1 predicts the mediator, which predicts y, and that pathway fully explains the relationship between x1 and y. And we've done that simply by constraining beta 1 to be 0. And we can write the equation for that, where now I'm saying y hat is equal to 0 times x1, because that's where I'd put beta 1, but I've changed beta 1 to 0, so I'm constraining beta 1 to be 0. So my model is that predicted y is equal to 0 times x1, in other words, that's just going to drop out of my equation, plus beta 2 times the mediator, plus beta 3 times x3. And note that my model for my mediator is still the same as I had it before, where I say the mediator is equal to this pathway here, beta 4 times x1, and this bottom pathway, x3 times beta 5, beta 4 times x1, and beta 5 times x3. So that's what a model would look like if I constrain a path to be equal to 0. Now, notably, if I ever needed to, this would be somewhat of an unusual situation, but if I ever needed to, I could constrain a path to be any value I wanted it to be. So maybe for some reason I wanted to constrain this pathway to be 0.43. If I wanted to, I could do that. For example, maybe someone else did a study and they found that that pathway was 0.43, and so I wanted to run my model under the assumption that their results were correct and see how that fits in my situation. So if I wanted to, I could constrain this pathway to be 0.43. And that we wouldn't do that type of constraint that often, but that helps to illustrate the types of constraints that we can put on models, and it illustrates the types of things that I mean when I say constrain. So in this case, I've constrained beta 1 to equal 0.43. Now, another type of constraint, and this is actually going to be a constraint we will use to test for a difference between two beta weights, is that we can make a constraint where we say two parameters have to be equal to each other. So I could make a constraint, and I could say this beta 1 could be any value it needs to be, but beta 1 and beta 3, these two betas have to be the same. They have to be identical values. So whatever beta 1 is, beta 3 has to be the exact same value. So in my model here, I take beta 1 and beta 3. They're still in my model, but I'm gonna make this constraint. I'm gonna say they have to be equal to each other. Whatever beta 1 is, that has to equal beta 3. Beta 3 has to equal beta 1, and so forth. So those are some types of constraints that we can put on our models when we run a structural equation modeling program. And as we'll see, this is where structural equation modeling gets really valuable, because we can do the two things we talked about. One, we can simultaneously estimate multiple equations. Like we see here, we've got actually two equations we're estimating at the same time. And we can put constraints on our models. So those are the two big advantages we get with structural equation models. We can do models that simultaneously estimate multiple equations and maybe even most importantly, we can put constraints on models. Okay, so I've been talking about how we can use a variance-covariance matrix to produce the parameter estimates in our structural equation model, but I haven't told you about how we actually go about calculating those parameter estimates. Exactly how do we use that variance-covariance matrix to produce our parameter estimates? And actually, I'm not going to quite tell you about that now. That's still coming up in just a bit here. Hold on for a moment. But before we get there, let's turn things around, and I want to show you how I can use a model to reproduce a variance-covariance matrix. So what we want to do is we want to use the variance-covariance matrix to produce our model, to produce the parameter estimates for our model. But once I have the parameter estimates for my model, I can use those parameter estimates in my model to reproduce the variance-covariance matrix. And so I want to kind of look at this backwards first, and then once we look at it from the backwards direction, we'll look at it from the forwards direction. So we're going to start backwards, and then we'll proceed with the forward direction. And when we're all done with this, it might make sense why I'm doing it that way. For right now, it might seem like an odd approach, but that's the way I want to do things. So I want to say I do a study, and I test this model that I have depicted in the top. And if you look at that model, you should recognize that's depicting a mediating relationship, where I've got a direct effect of x1 and y controlling for my mediator, and I've got a mediated pathway where x1 predicts my mediator, and my mediator in turn predicts y. And so that's depicting actually two different regression equations. There's one regression equation where x1 is predicting m, and a second regression equation where both x1 and m are predicting y. So let's assume that I've run my analysis in the way that I haven't told you about yet of how we actually do things, but we've got, say we've done it, and we've got our beta weights. We've got, say the beta weight for x1 and y, maybe that was maybe 0.3, and maybe this effect here, maybe that was 0.5, and maybe beta 3 was 0.2 or something like that. So say we've done our study, we run our analysis, we get our beta weights. And what I want to illustrate for you right now is that I can take this model with my parameter estimates and use that to reproduce the variance-covariance matrix. And how we go about doing that depends on my model. If I have a really complex model, the process of reproducing a matrix could get really complex. But let's take a simple model like this, and I just want to show you how the process in general, how it works using this example. So if I have this model, I need to get a variance-covariance matrix. It's going to be a 3 by 3 because I have three variables, x1, my mediator, and y. And so my variance-covariance matrix will be 3 by 3. And if I assume all variables are z-scores prior to analysis, then the variances are equal. Every variable will have a standard deviation of 1, and a squared standard deviation of variance will also be 1. So every variable will have a variance of 1. So I'll just put 1s on the diagonal, because all my variances are 1. That was fairly easy. Now, we need to get what is the covariance between x1 and m. In my model, notice that I say x1 predicts m, and it turns out this beta weight right here will be that covariance. In fact, recall that if I turn everything to z-scores prior to analysis, we're assuming everything z-scores, if you turn everything to z-scores prior to analysis, and I have an equation where I have one predictor and one outcome, a simple regression equation with just a single predictor, that my beta weight is the same thing as my correlation. And if everything's turned to z-scores prior to analysis, the beta weight and the correlation are the same as the covariance. So therefore, beta 3 is simply equal to the covariance between x1 and m if I'm assuming every variable, everything is z-scores prior to analysis. So I can figure out, based on my model, I look at beta 3 right here, and I know that that beta 3, that's what should be the covariance between x1 and m according to my model. Now I've got two other covariances I need to estimate, and from my model they're a little more complex, but not that much more so. So what about the covariance between x1 and y right here? Covariance between x1 and y. So according to my model, I've got the relationship between x1 and y. I've got this direct effect, which is beta 1, and this indirect effect, which is going through the mediator. And if you recall from our discussion of mediation in our previous unit, the total effect of x on y is equal to the direct effect plus the mediated effect. And if you recall, the mediated effect is equal to the product of your two mediated pathways. In this case, beta 3 times beta 2. The product of those two mediated pathways will be the total mediated effect, and the mediated effect plus the direct effect, beta 1, will be my total effect. And if everything's turned to z-scores, my total effect of x1 and y will actually be the covariance of x1 and y. So what I have down here is beta 1, that's the direct effect, plus the product of beta 3 plus beta 3 times beta 2, the mediated pathway. My direct effect, beta 1, plus the mediated pathway equals my total effect, which, if everything is z-scores and standardized, is the same thing as my covariance. So you see how we could use my model. I can predict, I can recreate and calculate what the covariance between x1 and m is, and I can calculate what the covariance between x1 and y is. And also it turns out, and if you think about it this way, you know that if we turn everything to z-scores prior to analysis, that x1, the beta weight for x1 predicting m, will be the same thing as the correlation. And we know that in a correlation, it doesn't matter, the correlation between A and B is the same as the correlation between B and A. So the correlation between x1 and m is the same as the correlation between m and x1. So this beta 3 right here, we know that if everything was turned to z-scores prior to analysis, that beta weight will be the same regardless if the arrow is pointing from x1 to m, or if I scribbled that out and put my arrow going the other direction, I would get the exact same beta weight. Because everything is z-scores prior to analysis, and if everything is z-scores, my beta weight for just a single predictor is going to be the same thing as a correlation, and the correlation will be the same regardless of which direction it goes. The correlation between x and m is the same as the correlation between m and x, and so I could reverse my arrow, and I know I would get the exact same beta weight. And so from that logic, we can say the total effect of m on y is equal to a direct effect of beta 2 plus a mediated pathway where I go m through x1 to beta 1, which is beta 3 times beta 1, which I have over here, beta 3 times beta 1. So we can say the covariance between y and m is going to be equal to beta 2 plus the product of beta 3 times beta 1. So what I've shown you here is that once I estimate my model and I get all my parameter estimates for my betas, I can use these parameter estimates to recreate my original variance-covariance matrix. So now I want to talk about something called degrees of freedom. And degrees of freedom in structural equation modeling is going to be a little bit different than what we've talked about before when we've talked about degrees of freedom. It's a little bit of a different type of animal, I suppose. So before we've talked about degrees of freedom in regards to sample size. So for example, in calculating a standard deviation, degrees of freedom is n minus 1, your sample size minus 1. Here, with structural equation modeling, it's something completely different. We're going to look at what is the relationship between the number of elements that you have in your variance-covariance matrix and the number of parameters that you're estimating in your model. So in the example we've been looking at, we've had 3 elements, 3 covariances in our variance-covariance matrix, and we have 3 beta weights in our model. And we've been talking about how we can use these beta weights to reproduce or recreate our variance-covariance matrix. We can use these 3 betas and recreate what these 3 covariances are. So degrees of freedom, if I take the number of covariances or number of elements in my variance-covariance model and subtract from that the number of parameters that I'm estimating in my equation, I will have degrees of freedom. And the example we've been looking at here, I have 3 elements, 3 covariances in my variance-covariance matrix that I can use to estimate my 3 beta weights, or as we've been looking at, we'll be using these 3 beta weights to reproduce our 3 covariances. And so in this example, the number of elements in my variance covariance matrix, in this case the covariances that I'm looking at, is equal to the number of beta weights. And so I will say I have 0 degrees of freedom. The number of covariances minus the number of betas equals 0. So I have 0 degrees of freedom. And when I have 0 degrees of freedom, I will call my model saturated. And there's a couple things about a saturated model. First of all, once my model is saturated, it means that if I use my model to recreate the variance covariance matrix, I will recreate it perfectly. If I accurately calculate my 3 betas here, and use those betas to recreate this model using these formulas I have down here for calculating each covariance, I will perfectly and accurately reproduce each of those covariances as they originally were in my data set. So when I have a saturated model, when I have 0 degrees of freedom, that is, when I have the same number of things in my variance covariance matrix as parameters that I'm estimating, then I have 0 degrees of freedom and I can perfectly reproduce my variance covariance matrix from my model. Note that I cannot have negative degrees of freedom. I cannot have more parameters in my model than I have elements in my variance covariance matrix. So, for example, if I wanted to say x1 predicts m, but there's also a correlation between x1 and m, I couldn't do that. I couldn't have both a beta weight and a correlation in my model. And you might have noted that in my models, whenever I've had a direct regression relationship saying that this x predicts this m, I haven't had a correlation between those two variables. And that's actually intentional. It wasn't a mistake or an oversight. It was actually intentional because you can't have both. Recall that if we calculate this beta and everything's standardized, our beta will actually be the same thing as a correlation. And so if we try to have a model where we say a beta and a correlation are two different things that could potentially take on two different values, we've created an impossible model. We couldn't possibly find single identified, we'd say the model's not identified. There would be not one single solution that would solve it. We could have many possible things that might solve our model. We've made an impossible model if we have negative degrees of freedom. So we cannot have negative degrees of freedom. In other words, we cannot estimate more parameters than we have elements in our variance covariance matrix. However, we can have positive degrees of freedom. And this brings in that issue of constraint. Recall that we can put constraints on our models. We could constrain a beta to be 0. We could constrain a pathway to be 0. Or we could constrain two betas to be equal to each other. And this is where things get really interesting. When we put constraints on our models, we have fewer parameters than we have elements in our variance covariance matrix. So for example, if I constrained this beta, beta 1 to be 0, and in this case I'd be testing a full mediation pathway where x1 predicts m, which predicts y, and the full effect of x1 and y is explained by m, and there's no residual direct effect here. I've set that effect to be 0. That in this situation, to estimate this model, I only have two betas, beta 2 and beta 3, and I'm not estimating beta 1 because I've assumed that's 0, so I'm not going to get an estimate for that. So I just have two betas in my model. So in this case, I'd be trying to reproduce a variance covariance matrix that has 3 covariances, but I'd be doing that with only 2 betas. So I have fewer parameter estimates than I have elements in my variance covariance matrix. And this is what makes things really interesting. We're able to test important things when we put our constraints on our model. And part of the reason why we're able to test these things is because we now have positive degrees of freedom. We're trying to estimate a variance covariance matrix using fewer components than the maximum. Now, if I put constraints on my model, if I have positive degrees of freedom, that's where things get really interesting. Because if I try to use this model, these beta weights in my model, to reproduce my variance covariance matrix, and if there are constraints on my model, then I'm not going to be able to perfectly reproduce that variance covariance matrix. There'll be some error in my attempts to recreate it. So I cannot perfectly reproduce a variance covariance matrix if I have constraints on my model. Let's see how this would work in this current example. So the covariance between x1 and m is simply equal to beta 3. That's still the same as before, and that we can estimate that accurately. So that's just fine there. But what about, say, the covariance between x1 and y? We saw before that was equal to beta 1 plus the product of beta 3 times beta 2. It's the product. We have our direct pathway plus our indirect pathway, and you add those two together, that gets the total effect of x1 and y. But in this model, if I constrain beta 1 to be 0, what I'm saying is that direct effect is exactly 0. And so if it turns out that effect is anything but 0, if there's a little bit of a pathway there, then this formula at the bottom is not going to be the correct way to estimate the total effect of x1 and y. It was not the correct way to estimate the covariance if that pathway is not 0. So if I put the constraint on my model and say that pathway is 0 and use this formula to estimate that covariance, I'm going to be a little bit off. There's going to be a little bit of mistake when I try to estimate that covariance because I'm assuming that beta is 0, and if it's not actually 0, this formula isn't going to be perfectly correct. And likewise, it's saying here that there's no mediated pathway there. It's saying that if beta 1 is 0, then m can't lead to y through x1. So there's no mediated pathway that direction. The only effect that m has on y is through beta 2. And so it's just saying that effect here, beta 2, the covariance between m and y is simply equal to beta 2 and nothing else. And again, if there happens to be any residual mediated pathway, then this equation I have here would be a little bit off. So when I put constraints on my model, then it means that my the variance covariance matrix that I estimate from my model will not be perfect. So putting this all together, we can talk about two different types of variance covariance matrix. So I'm going to use the regular English letter capital S here to be the symbol for what I'll call the sample covariance matrix. This will be the actual variance covariance matrix that we get from our sample. I do a study, I collect data from people, and we get the actual variance covariance matrix, and we print that right here, and I'm going to call that S. So S is the actual observed sample covariance matrix. And then if I run my model and calculate my parameter estimates, like my betas, and then use my model to reconstruct my variance covariance matrix, I'm going to use the Greek sigma symbol to indicate my reconstructed variance covariance matrix, the one I reconstruct on my sample. And here I have how I would do that in my previous example. If I have testing a mediation pathway with x1 and a mediator predicting y, and I'm constraining it to be fully mediated such that the pathway beta 1 is constrained to be 0. And so here is how we would calculate those covariances in that model with a constraint on it. And because I have a constraint, what that means is S will not equal sigma. My sample covariance matrix will not be the same as my reconstructed. Now, if I had a saturated model, if I had 0 degrees of freedom, if I was estimating the same number of parameters as I had covariances in my model, then I could perfectly reconstruct it. Then in that case, my reconstructed matrix would be identical to my sample covariance matrix. But because I've put constraints on my model, these two matrices are going to be different from each other. I have the actual observed one, what I actually got, and below I have the sigma, the reconstructed matrix, the matrix I estimate based on my model that has constraints on it. So now I'm getting really close to telling you how we calculate those betas. Not quite, but really, really close. So when I have these two matrices, I've got my S, my sample variance covariance matrix, and my sigma, the reconstructed covariance matrix, and I've noted that if I have constraints in my model, my sigma will not be the same as S. My reconstructed matrix will not be identical to my sample one. But if I have a saturated model with 0 degrees of freedom, then they'll be the same. So once I have my sigma, my reconstructed variance covariance matrix, I could calculate something called a likelihood. And the formula for calculating a likelihood actually gets rather complex. And I'm not going to mess with that formula here, but I want you to know that we can calculate this formula called a likelihood. And the likelihood is simply a formula that gives us a value indicating what is the likelihood of obtaining S. That is, what's the likelihood of doing my study and getting this variance covariance metric right here, the one I actually got. So what's the likelihood of doing my study and getting this covariance matrix that I got, assuming that sigma is actually a model of the true population parameters. So in other words, if I assume that sigma, right here, if I assume that's actually what the true population is, if I assume that in the population, if I were to sample everybody in the world, this is actually what the true population parameters are. If this is really what the covariance between x1 and m is, if this is really a 0 plus the product of beta 3 times beta 2, if that really is the value I get for that when I estimate that value, if that really is the true covariance in the entire population, and when I estimate this covariance right here, the covariance between m and y, and whatever covariance I get for that, if that really is the true covariance in the population. So if I create this sigma covariance matrix and get the values for that, and now I'm going to assume that this covariance matrix is the true parameters in the population, that covariance matrix is an accurate, perfect model of exactly what it's like in the population. So if I assume that sigma reflects what it's really like in the population, what is the likelihood of getting what I really got, the actual sample matrix that I got in my study? What's the likelihood of that? So we can calculate this value that's called a likelihood that tells us what's the likelihood of getting the sample covariance matrix that we got, given the assumption that the reconstructed covariance matrix is actually a perfect model of the true population parameters. So now I'm ready to tell you how we actually estimate our parameters in a structural equation modeling approach. Recall that with regression, we talked about least squares regression, where we use formulas to calculate an intercept and a slope that will minimize the sum of the squared errors. So we're going to use a slightly different approach with structural equation modeling, in that we want to figure out what parameter estimates, for example, what beta weights, will produce the maximum likelihood. That is, if we're going to estimate what is the likelihood of our sample results, the results we actually got, the results we actually observed, what is the likelihood of our results given our reconstruction, given we assume that our reconstructed matrix is an actual model of the population parameter, we want to figure out what model the population parameters will produce a variance covariance matrix that gives us the highest maximum likelihood value for the sample covariance matrix that we actually got. So we want to figure out what parameter estimates, what beta 3 and beta 2 in this example, will produce a maximum likelihood value. That is, we want to estimate the likelihood is the estimate of obtaining S, our sample covariance matrix, assuming sigma, our reconstructed covariance matrix, is the true population parameter. And so we want to figure out what model will have beta weights, will have parameters that will create a reconstructed matrix that will give us the highest, the best possible likelihood value for S. So putting it all together, we can compare how we calculate parameter estimates when we're doing ordinary least squares regression and how we calculate parameter estimates when we're doing structural equation modeling. With ordinary least squares regression, if you recall from our previous units when we talked about regression, we calculate intercepts and slopes that will minimize the sum of the squared error. The formulas that I gave you for calculating intercept and slope, if you plug those in, you will produce equations that will minimize the sum of the squared error. In contrast, when we do structural equation modeling, we want to identify parameter estimates that will maximize a likelihood value. We want to calculate beta weights and other parameter estimates that will produce the highest possible maximum likelihood value. Now, how do we go about doing this? Do I have equations that I can give you to calculate beta weights and parameter estimates to maximize a likelihood value? Well, not exactly. When we're doing structural equation modeling, we're going to use the computer to help us out. We're going to ask the computer to figure out what parameter estimates will produce the highest possible maximum likelihood. And the computer is going to use somewhat of a trial and error process. It's going to go through iterations. It will try out some different values for beta weights and see what the maximum likelihood value is for that model, and then it will test some different values for those beta weights and see if that makes the model better or worse, and it will keep on tweaking and adjusting the model until it identifies a set of beta weights and parameter estimates that produce the highest possible maximum likelihood value. So it's an iterative process that the computer does, not something we do by running equations. There actually are equations that the computer uses to do that iterative process, but it's not something you would want to attempt to do by hand. And so that is how we get the parameter estimates when we're doing structural equation modeling. So once we have used maximum likelihood to produce our parameter estimates, we will have a reconstructed variance-covariance matrix that comes as close as it possibly can to the actual observed sample variance-covariance matrix. That's what maximum likelihood does. It produces a reconstructed variance-covariance matrix that comes as close as possible to the actual observed sample variance-covariance matrix. So at this point, we can ask the question, how close does it come? Does our reconstructed variance-covariance matrix exactly reproduce the sample matrix, or does it reproduce something that comes very, very close to the actual sample variance-covariance matrix? Or does it reproduce something that is substantially different from the sample variance-covariance matrix? And this is essentially a question of fit. So questions of fit all involve a question about what is the size of difference between our sample actual observed variance-covariance matrix and sigma, our reconstructed variance-covariance matrix. And there are several different ways to define fit. That is, there's different ways to calculate the size of difference between these two matrices. And we're going to talk about some of them. But at this point, just note that they all involve a question about what is the size of difference between S and sigma. What is the size of difference between our sample variance-covariance matrix and our reconstructed variance-covariance matrix? Now, questions of fit become especially important whenever we put constraints on models. Recall that if I don't put any constraints on a model, I'll call the model saturated and it has 0 degrees of freedom, and our reconstructed matrix will exactly reproduce the actual sample matrix. So in other words, if I have a model that has 0 degrees of freedom, it's saturated, I have no constraints on it, then the fit will be perfect. The reconstructed matrix will be identical to the actual sample matrix. So questions of fit become important when I put a constraint on a model, because once I put a constraint on a model, I can then ask the question, how well does a model fit when I put this constraint on? If I put a constraint on a model and I find that my reconstructed variance-covariance matrix still comes really, really close to the sample matrix, I will say that constraint is a reasonable constraint to make. My model is working well, and that would provide support for the model as I specified it with those constraints. On the other hand, if I put a constraint on a model and that makes a reconstructed matrix that is substantially different from the sample matrix, I would say that constraint is causing problems. That constraint should be rejected. That constraint is not working. So a good fit means there is a close match between these two variance-covariance matrix, and that would provide support for my model. It would provide support for the constraints that I have put on the model. It would say those constraints are reasonable and everything is still working well in spite of the constraints. On the other hand, a bad fit means that there's a substantial difference between these two variance-covariance matrices, and that would mean that the constraints that I'm putting on the model are not reasonable. It would fail to provide support for my model. It says my model should be rejected and I should not be making those constraints that I made. So we use fit to evaluate the constraints we put on a model. A good fit provides support for the constraints. It says those constraints are reasonable and the model is still working well. A poor fit means those constraints are not reasonable and should be rejected. We should not be making those constraints if we find a model has a poor fit. So we use fit to evaluate the constraints that we put on our models. So now let's look at some different ways that we can assess fit. One way we can assess fit, which is probably the approach that's been around for the longest time, is to do something called a chi-square significance test. Now what we're going to do is test for a significant difference between S, our sample actual observed variance covariance matrix, and sigma, our reconstructed variance covariance matrix based on our model. And in this case, if we have a significant result, it means there is a significant difference between these two matrices. A significant chi-square means that your reconstructed covariance matrix is significantly different from your sample covariance matrix, meaning you have a bad fit. So with a chi-square significance test, a significant chi-square would be indicative of a bad fit, and a non-significant result would be indicative of a good fit. And as we'll see, this is actually another example of a significance test turned upside down on its head, and for that reason it's not always appropriate, but actually there are a few situations where it works well for us. So recall that with significance testing we have a null hypothesis, and the null hypothesis is an assumption about what the true population parameters are. Usually when we do significance testing, the null hypothesis is that all the population parameters are 0. But in this case, what we're going to do, our null hypothesis is that the population parameters will be whatever sigma says they are, what our model, with all of its constraints, says those population parameters are. So we assume that our model is a true model of the population parameters, and then we test the extent to which S, our sample covariance matrix, differs from that true population parameter. And given the size of our sample and given the size of the difference, if we have a significant difference between the two, that means we should reject our model. We should reject the model and all the constraints that we have. So we should reject sigma, this model we created with the constraints we made. If we have a significant result, it says we should reject that model and say those constraints are not working. They do not do a good job of modeling the true population parameters because we got a sigma that's so wildly different from what we would have gotten if that model was true. Now, for the most part, like I said, this is a significance test turned on its head. And so if I had a model and I was hoping to support my model, so if I was wanting to find support for my model, this would not be a good approach to take because, again, the smaller my sample, the less likely results are to be significant because this chi-square test still does take into account sample size. And so if I have a huge sample, and actually when we're doing structural equation modeling, we often need large samples, and it's actually fairly rare to have a non-significant chi-square test. These tests are actually almost always significant. But one exception where it might not be significant and where it actually gives us useful information are situations where I have a model I'm actually wanting to reject. And that's what we're going to do to test for the significant difference between two betas. Now we're actually at the point, when we started this whole unit, the whole purpose of talking about structural equation modeling was to test for a discriminant validity, where I wanted to see if there's a difference between two betas and the magnitude of effect when they're trying to predict some outcome variable. So if I do a model where I constrain my two betas to be equal to each other, in this case, my null hypothesis is that the betas are equal. That's the sigma is going to be reconstructed based on my constraints where I'm constraining my betas to be equal to each other. And in this case, if I calculate a chi-square and get a significant result, it means I should reject that null hypothesis. That is, I should reject my model that constrains the beta to be equal to each other. And if the only thing I've done in my model is constrain the betas to be equal, and it's a significant result, meaning that model needs to be rejected, then it means the assumption that the betas are equal is incorrect. It's a bad assumption. It's not working well, and I need to reject that assumption. So in this case, this is actually one place where a chi-square is useful, is if I can do a model, constrain my two betas to be equal, and if I get a significant chi-square, it means that the two betas are actually significantly different from each other, and I would take that as evidence of discriminant validity. So that is how I would use structural equation modeling to test discriminant validity. So I mentioned that I would not use a chi-square significance test in a situation where I had a hypothesized model that I was hoping to support. And this is the most common type of situation when I would use structural equation modeling, is when I'm trying to support a model. I have a hypothesis about how variables should be related to each other, and I'm hoping to find support for my model. So how would I assess fit in that situation? So in this situation, I would use something called a fit index. And there's actually many different types of fit indices, and we're going to get into those in more detail in a later unit. But for now, let me give you just a brief overview that a fit indice or a fit index is something that measures the extent of fit. That is, it's going to measure the extent of similarity or difference between our S matrix, our sample variance covariance matrix, and sigma, our reconstructed variance covariance matrix based on our model. So all measures of fit are one way or another, they're going to involve looking at the difference between these two matrices. And there's many different approaches to doing that, but they all boil down to looking at the difference between those two matrices. Fit indices, unlike a chi-square, are not going to be influenced by your sample size. So they're going to give you a value that's like a descriptive value that will say to what extent does this model fit the data. And again, that's what I would use. This is what I would use if I have a hypothesized model I'm hoping to accept. I would use one of these fit indices. And again, I'm not going to get into them too much detail right now, but we will talk about these a little more extensively in a later unit. But at the moment, let me just give you an overview of some of the most common types of fit indices, or some of the most important ones, and ones we will be talking about later. So one is called a comparative fit index, and another approach is called the root mean square error of approximation, and a third approach is called the standardized root mean residual. And that's just giving you a taste of something to look forward to. We're going to talk about exactly what those things do later on. But for now, note that each one of those is a measure of fit. They're going to give us a value that will tell us the extent to which our S matrix, our actual observed covariance matrix from our data, is similar or different from our reconstructed matrix based on our model. And that's what those will do. So now you have everything you need to test for a difference between two betas. So for example, if I wanted to validate a pair of scales, maybe I have my collaborative engagement scale and my adversarial engagement scale, and I thought that collaborative engagement should produce a weaker effect in predicting perceived threat, and that adversarial engagement should produce a stronger effect in predicting perceived threat, then I could run a regression equation where I use both collaborative engagement and adversarial engagement to predict perceived threat. And in structural equation modeling, I could constrain those two beta weights to be equal. And if I get a significant chi-square, it would mean I have a significant difference between the two betas. The magnitude of effect between the two betas is not the same, and that would give me evidence of discriminant validity between my two scales. A few things to note when you're doing this. One is that the two scales, it's important to make sure you're measuring both variables using identical units. If you're not using identical units, then you can't compare them. And the best way to do that is simply to standardize your variables, make sure everything is turned to z-scores prior to analysis so that you're measuring both scales in standard deviation units. The process, you would start off using SEM, and I would use structural equation modeling to estimate an unconstrained regression model. That is a model where you don't put any constraints on it first, and see what you get when you estimate an unconstrained model. And actually, when you do this, your unconstrained model using structural equation modeling will be nearly identical to the results you would get if you simply used least squares regression, the typical approach to running a regression analysis. The unconstrained model, that's the one where you have 0 degrees of freedom, your model is completely saturated, and so that means that your model reconstructed variance covariance matrix will be an exact replica. You will exactly reproduce your actual data variance covariance matrix when you have a saturated model. Then you will put one constraint on your model. You will constrain your two betas to be equal to each other. And that will actually produce a model with 1 degree of freedom. When you put one constraint on, you will have 1 degree of freedom. And you will estimate that model with that constraint. and then use the chi-square test to see if you have a significant difference. And if that chi-square is significant, it means that that constraint created a very bad fit, and so that constraint needs to be rejected, meaning you have a significant difference between the two betas. It does not work to constrain them to be equal, therefore they must be different. And so if you have a significant chi-square, that would be evidence of discriminant validity. Remember that when we're doing tests for differences between effects, we want to know what is the difference between the effects and the absolute magnitude of effect. And so we don't want to have positive and negative signs interfering with these results. So if you have a situation where you have two betas and they're going in different directions, if the signs differ, if one of the beta is positive and one is negative, you need to go back and reverse score one scale so that both your variables are scored in the same direction. So if you run a regression and one beta has a positive value, the other has a negative value, it probably means you need to go back and reverse score one of your betas so they're both going in the same direction, so that you can test for a difference in absolute values and not have your results messed up by the fact that they're scored in two different directions. And again, your final result is simply we're going to look at that chi-square difference test, which will have 1 degree of freedom, and it's testing the null hypothesis that the betas are equal. So if you have a significant chi-square, you need to reject that null hypothesis and conclude that your betas are different from each other, and that is what we're looking for in terms of demonstrating discriminant validity for your variable. So if significant, conclude the betas are different and that you have different effects for each of those two variables. And that is everything for Unit 10.